So let us next continue our section with the definition of Cauchy sequences. If you remember, long ago we defined Cauchy sequences of rational numbers in, let me just see the number, in definition 518. So we are going to now do that same thing but now in a general metric space. So this is the definition. Let xn be a sequence in a metric space x comma d. You already know what the individual parts of this notation mean. And we call this a Cauchy sequence if for every positive real number epsilon there exists an integer n, capital N, which is at least as large as the starting index. This m is of course some integer such that the distance between the terms xj and xk of our sequence is at most epsilon, that is less than or equal to epsilon, for all j and k which are at least that stage, that capital N. If you go back to that definition, you would see that this is just that definition. The only difference is that here we are using the metric d to measure distance, whereas for sequences of rational numbers we used the ordinary absolute value metric. That's the only difference. Oh, there is one more difference. Actually, I used this ordinary less than or equal to inequality here. I did not use the strict inequality, strictly less than epsilon. If you see the text, you will see that the text uses strict inequality. You don't really gain or lose anything if you use the strict inequality here or this one. Ultimately, a sequence is a Cauchy sequence in this sense, if and only if it's a Cauchy sequence in that sense where we use strict inequality. So that does not ultimately make any difference. And next we have this result which we also saw back then when we introduced ourselves to Cauchy sequences of rational numbers, that any convergent sequence is a Cauchy sequence. That same is true here also. Convergent sequences are Cauchy. Let xn be a sequence in a metric space which converges to some point of course x naught in x, then xn is also a Cauchy sequence. And we are going to see the proof in exercise 12.4.3. That means we have to prove it ourselves. And then we have this other fact also. One can also verify that any subsequence of a Cauchy sequence is itself a Cauchy sequence. And I leave it to you to see how to in fact prove it. I think we did it for sequences of rational numbers. So you can go back and see how we did that. But not every Cauchy sequence is convergent. That means this is the converse statement to that lemma. That is not true. I mean, that's not always true. And to illustrate that, we have this example, which has been called an informal example by the author because the sequence that you see here has not exactly been formally defined. I mean, it's just something that we know from experience about what? About the number pi. So these are the rational approximations to the number pi with more and more digits. For example, it starts with 3 and then the next term is 3.1, then 3.14, 3.141, 1415, and then I think 9 comes, something like that. So in that sense it is informal because we are not exactly rigorously saying what the next term is or what the one after that is. But you get the point. I mean, this is something you already know. So you consider this sequence and it's obviously a sequence in the metric space of rational numbers with the usual absolute value metric. This sequence is actually a Cauchy sequence, but it is not convergent in this metric space because the limit of this sequence is pi, which is not a rational number. It's a real number outside the metric space of rational numbers. It's irrational. And that is why, in spite of being Cauchy, it's not convergent. So the converse, that means this statement is not necessarily true. So that example shows that, we do not see here anymore because I wrote other things. That example shows that not all Cauchy sequences are convergent. However, if even a part of a Cauchy sequence converges to some point, then the entire sequence converges to that point. This next lemma is about that. Let Xn be a Cauchy sequence in some metric space x comma d. And suppose, what do I mean by, or what does the author mean by a part of a Cauchy sequence? That is a subsequence. If it has, that means if this sequence has a subsequence which is convergent and converges to some point x naught in the space, then the entire sequence also converges to that same point x naught. And for its proof, we have to wait until we solve this exercise 12.4.4, which we will do once the section is over. We will start solving the exercises. So there we will prove all these things. So the example we saw today, that means example 12.4.8 shows that not every Cauchy sequence is convergent in the space of rational numbers with the usual metric. But you recall theorem 6.4.18, which we proved when we, chapter 6, this is the chapter where we studied sequences of real numbers. Here we proved that every Cauchy sequence of real numbers is convergent. So in the metric space of real numbers with the usual metric, it's a different case. Okay, here you need not think about having or not having convergence if you have a Cauchy sequence. All Cauchy sequences are convergent. And this fact leads to the next definition that we are now going to see. And that definition is this, the definition of a complete metric space, which you can guess what it is. A metric space x comma d is called complete if every Cauchy sequence in it converges to a point in it, like this space. So that means this is not a complete metric space, but the space of real numbers with the usual metric is a complete metric space. And this completeness property is in fact the reason for constructing the system of real numbers from the system of rational numbers in the first place, so that Cauchy sequences have limits, so that we don't have to think about whether a Cauchy sequence has or does not have limit when you want to do something with Cauchy sequences. Actually, why do we need these things? We need these things, we need sequences because sequences provide us with approximations to complicated objects. For example, an irrational number is a more complicated type of number than rational numbers. Rational numbers are easier to understand. They are ratios of integers. So although you don't have a description like that for irrational numbers, but what you can do instead is you can approximate an irrational number with a sequence of rational numbers, where the terms of the sequence get closer and closer to the irrational number. So in that sense, sequences provide us with simpler things to approximate a complicated thing. Now, if you are working with a sequence of simple things, and that is Cauchy, that means its terms are getting closer to each other, then you would want to know whether it is really going to approximate something complicated. That something complicated should be there in the space, but that is not always in this space. So that is why you have a problem in doing analysis if you only use rational numbers, or in fact doing calculus. That is why we need real numbers. So that is the significance of complete metric spaces, that they are complete in the sense that whenever you want to do approximation using sequences, the ideal object which is being approximated is always there for the type of sequences which should be used for approximation, that is Cauchy sequences. After this definition, the next item, that is item number 12.4.11, according to the scheme for numbering items in this book, is an example which just says that thing, but what I said just now, that the metric space of real numbers with the usual metric is complete, but the metric space of rational numbers with the usual metric is not complete. So I thought of not writing that. So instead, let's now see in this next proposition something which is very nice about complete metric spaces, those metric spaces which are complete, like the space of real numbers. And that statement is this: let x comma d be a metric space which is complete. Okay, we are starting with a complete metric space, and let y be a subset of x. If this subspace is complete as a metric space, if this subspace y is complete, then the subset y is closed in x. It's a closed subset of x. You do understand what this notation is. I mean, you recall that this is the restriction of the metric D to y times y Cartesian product y. You actually recall what D is. D is a function whose domain is the Cartesian product x times x. So D takes in as an input an ordered pair of points from the set x and gives a real number as its output. That real number is interpreted as the distance between those chosen points. That's what D is. D is a metric, it measures distances between points chosen from the set x. Now, y being a subset of x makes this Cartesian product y times y a subset of x times x. So, if you restrict D to that subset, which makes sense because this is a subset of the domain of D, and the domain of D is x times x. So then you get this restriction, which is also a function, but this time it has this product as its domain and the range is the set of real numbers. So that way we get another metric space which is sitting inside x. So it's a subspace. If this subspace is complete, the original space is complete, and if the subspace is also complete, then y as a subset of x has to be closed in x. And part B just says that the converse is also true. If y is closed in x, then this subspace is complete. And for proof, we will see exercise 12.4.7, which of course is going to ask us to prove this. That's just it. So we learned that not all metric spaces are complete, although some are. And as a closing remark, the author says this: say you start with an arbitrary metric space x comma d. Then there always exists a larger metric space, which he denotes like this: x bar comma d bar with its own metric d bar, larger in the sense that this is a subspace of this. This is sitting inside this, and this d is obtained from this metric d bar by restricting d bar to x times x, just like this one. And this metric space is complete, the larger one is complete. If so, and that always exists, we call this larger one a completion of the original metric space. For example, R is one possible completion of Q. Actually, if we include the metric, the usual metric D, which is what we are talking about here, that Q has, then of course we have the usual system of real numbers with its own metric, which is an extension of the metric that Q has, as a completion, as the completion of Q comma D, where D is the usual metric. But the reason the author says it is one possible completion is that there are other completions also. So that's how you get p-adic numbers, and there are many other things. So this is where the section ends, and in the next video we will start solving the exercises.